Thank you. Thank you for the introduction. My name's Emily Gorcenski, and I'm going to be talking about going full stack with data science. Full stack is not a phrase that we hear very often in regards to data science, and I confess that I kind of put it in the title as a little bit of a hook to get you interested in the topic. But I want to kind of set an intention for what this talk is. My goal here is to talk about data science as an integral component of a team in an organization that is inseparable from all of the other components of your organization, your engineering teams, your design teams, your QA teams, and your customer relations, legal compliance, all of those things that we have heard about and talked about throughout this conference, and how to integrate data science with that very effectively. This talk comes from a place of having many, many discussions with data scientists in organizations of all shapes and sizes, and hearing many of the same problems over and over and over. Some of them dealing with the difficulty of productionizing our work, some of them dealing with the difficulty of convincing our stakeholders of the value of what we do. So if you're looking for like some really great technical, marvel, I don't have that here. What I'm hoping that you take away from this talk is a way to structure your work as a data scientist and to really advocate for yourself and for your teammates. There we go. Now it's working. So a little bit about myself. I am a mathematician by degree and an aeronautical engineer by training. I've been working in data science for the last couple of years, and I'm also a political activist by necessity. All three of those things are important. All three of those things have informed this talk. And by way of a small plug, I've co-authored a chapter recently for the book that's coming out by David Blank Edelman. The book is called Seeking SRE. SRE stands for Site Reliability Engineering. It's a different topic than most data scientists are involved in, but hopefully you'll see the parallels in this talk with some of the techniques and practices that site reliability engineers have developed over the course of their profession. And I wrote this chapter with my very good friend Liz Fong-Jones about organizing in the workplace and understanding how the work that we do intersects with society at large. So there's my little plug for you. So let's start with an example. Suppose that you work for a social media site, and your CTO calls you into a meeting and says, hey, you're the data scientist. We've got this problem. There's a lot of hate speech on our platform, and I need you to fix it. What do you do? Anybody? Shout out an answer. I'm an anarchist, so whoever shouts first and loudest is the winner. Machine learning. Okay. So we're going to machine learn hate speech out of our platform. Any specific ideas? Any techniques that we've learned about this weekend? Sentiment analysis. There we go. Okay. So your CTO says, we need to identify hate speech on our platform and prevent it. And you say, okay, that's great. I've got this algorithm with sentiment analysis. The problem is that's not the solution that the CTO is asking for. That's how to identify hate speech in your data. What the CTO is asking for is how do you identify hate speech on your platform? And those are two very different problems. Because it's one thing to work in data. It's another thing to be able to take your data and build it into a comprehensive, effective tool, product, or feature with your platform, service, or organization. So let's talk about what full stack means. And in order to do this, we're going to time travel a little bit back to 1998. And I picked 1998 because there's a joke that says that full stack is wherever the top of the stack is when you started your career to wherever the top of the stack is now. And I started my career sort of in 1998, and maybe you don't believe that I'm old enough to do that, and I actually have found a fountain of youth, and I will confess that it is a bit of a commitment, so I don't recommend it unless you need to. But 1998, what was the web looking like? The web was mostly static content. We had some dynamic tools. There was some dynamic development going on in the web. And it was things like CGI. We had like early PHP, like PHP 1 and 2. ASP before .NET existed. There was ASP 1 and version 1 and 2 existed before .NET was even in its beta. SHTML, Cold Fusion, all sorts of all these technologies. And clouds, like that concept was a weather. That was like a meteorological term, which may seem strange nowadays. But because of these technologies, because this was something that was really evolving rapidly, there were a lot of really bad practices. And so I dug up some 20-year-old code. And this is a game called Point Out the Code Sin. So this is code that I actually wrote for this gaming site that I made when I was 20 years ago old. And this is, like, these are practices that they advocated for in books, like table-based layouts, absolute positioning. This is like, I guess CSS did exist, but we weren't using it. That's a database query in a view component with, I think that's a password in the source code. And then there's like a SQL injection vulnerability sitting right there. So like this was common stuff. And what happened was people wrote a lot of this code and it was terrible. And as the internet grew and users grew exponentially, it didn't scale. And so we came up with this idea of separating concerns into a stack. So that you have your back-end development, your front-end development. And this is sort of the paradigm that has carried forward and still exists today. And in the late 90s, early 2000s, there were a couple things happening in the technology industry. One of them being that Java was kind of the dominant language within the software engineering enterprise space. You also had like a lot of people making a lot of money in COBOL because of Y2K. But if you weren't doing Y2K remediation, you were probably writing Java if you were in a software engineering field. If you wanted to be like the cool hip person. Like Java EE back then was like, I don't know if you're like a React developer now. So we kind of separated these components, and one of the paradigms that came out of this was model view controller. There's also a model view view model, which is a terrible phrase. There's database layers, and then there were middleware, and there was all sorts of stuff. And so we've, over the course of several years, developed this idea of separating concerns and removing your view components, your front-end components from your database, from your all your architectural code. And so we came up with this vague split between back-end and front-end web engineering. But if you look at a typical tech company now, there's so much more than just back-end and front-end. And we don't typically include this in our definitions of full stack. Like if somebody says, oh, I'm a full-stack engineer, like you should start quizzing them on security and infrastructure and DevOps and design and compliance, because all of those things are necessary components to actually deploying our tech stack. The question is, when we have all of these separations of roles that have exploded over the past several years, where does data science fit in? And that's a question that a lot of organizations are really struggling with. Like, we want to be able to make use of our data. We want to build products that can use data. But we don't really know where it fits into this very deep, convoluted scheme that we've made of how to separate roles. And so, like, depending on what your organization might do, data science can fit in all over the place. Some organizations, it's in front end, like they do smart UX, they do tracking. Some data scientists are just doing analytics. You know, they're not really a data science team, they're a data analytics team. Some of them are doing back end. You have like a model, you write it up, maybe you're doing fraud detection or something like that, and then you write up a bunch of code, and then you deploy a microservice. And then some companies like IoT, there's a lot of this work, doing streaming transformations and building out your infrastructure to train and deploy models in sort of an automated continuous delivery sense. So data science really does fit all over what we call the tech stack. So here's a question for you. Raise your hand if you're a data scientist and you have to do on-call shifts. That's one person, 1.5 people. One person's kind of like, yeah. Okay, so like most data scientists don't have to do on-call shifts. And why do I bring this up? It's because if we want to actually build models and have them in the critical pathway of our systems, if we really want to make data science valuable, we need to think about putting ourselves in that role and making data science inseparable from the rest of our stack. So it means that there's a future where if you're the data scientist, you get called up at 4 in the morning to do some emergency calculus. So typical organizations will have the data science doesn't work like a stack. In the ideal scenario, it works more like a cycle. And depending on your organization, it could be that most of your work is in algorithm development. There's lots of really cool talks here about computer vision and NLP and stuff like that. Maybe that's where you focus. Or maybe you're doing more feature engineering and you really don't need to use the latest and greatest, but you can get a lot of value out of just some linear or logistic regression with your data. The problem is all of your data is kind of a mess. Or maybe you're doing model building and your organization has picked a type of model and you're just working through your data and automating processes to deploy that technology. Or maybe you're doing product development, maybe you're doing analytics. But the point is that this is a feedback cycle. So if you want to develop a feature that makes your product better, you need to use data in some intelligent way, you need to go through this whole cycle because you need to get that feedback from when it's deployed, how are people using it, is it actually giving us the value that we are looking for out of that feature. So what does this mean in terms of full stack? So what is our full data stack? I'm not going to read through all this, but it could contain many things, from building measurement and data collection techniques, instrumenting our web views. It could be building experimentation like A/B testing, but better than A/B testing. It could be going through and doing machine learning. It could be building dashboards and communicating to stakeholders. Lots of things. And so as a data scientist, you might have to be good at a whole host of skills, from doing computational math to actually robust software engineering to database modeling, or even dealing with GDPR type stuff, ethics and compliance, and business cases. So a data scientist has to have a lot of skills. To give an example, this is a data science stack that I have some familiarity with. The number of technology components that we had in the stack, if you were to look from the minute that we collected data on a user to the final result of using that data, we started with basic math and stats, Jupyter notebooks, throwing SQL at things. We had multiple databases, Postgres in production, Redshift for analytics. We had Kafka doing stream processing, all sorts of stuff. We had a fully Scala backend, and then some Python tooling on top of that to handle our data, all the way down to actually using Salesforce, and there were even Excel spreadsheets that we had in the stack. So this is like a massive amount of knowledge that any one person would have to have. The good news is that there's no such thing as a full stack data scientist. So if that's giving you anxiety, great. You don't have to worry about all of those things. There's no such thing as a full stack engineer. And anyone that tells you that they're a full stack engineer is really minimizing the contributions of all of the people around them that are making the technology work. But we can build full stack teams, and so that's what the last part of this talk is about. And so that was a long-winded introduction to what I really want to talk about, which is a model for how to build a full stack data science team. So these are the Mars rovers. These are 3 generations of Mars rovers. There's the little cute one, which was named, what was its name? I forget. Sojourner? Was that Sojourner? That was Sojourner. And then there's Spirit, I think, or one of the Spirit Opportunity rovers, and then Curiosity. And so this is a test that NASA ran, testing these rovers in the desert, I think in Arizona in the United States. And this is interesting because in order to validate the technology, NASA had to take these rovers and create an environment that was similar to Mars, except we're on Earth, we're not on Mars, so it's very difficult to find that environment. But there's no way that they could launch a multi-billion-dollar device to another planet without having tried to at least validate it in a realistic environment. And so in order to measure the development of complex systems, in the 1970s, NASA developed something called the Technology Readiness Level scale, or TRL. TRLs were 9 levels of technology readiness, from 1, which represented basic research, to 9, which represented a system being proven in an operational environment. And these models were really useful to target where you were in the development process of complex systems. And these models, if you have been a government contractor, particularly in the United States, as I have been, when you do research, oftentimes when you write the grant, you say, okay, at the end of this research cycle, I expect to deliver technology at a TRL level of 4 or 6 or whatever it might be. And the purpose of this is not to, it is a little bit to deal with legal stuff and grantsmanship and all that, but it's really to be able to have a consistent way of communicating across teams where you are in your development process. And so we can take this and adapt this to our industry. And this is something that we don't often do in our Agile/Kanban/Scrum type of universe. But this TRLs were adapted by many different engineering bodies over the years. And this is a European Commission model, which I think is really useful because it maps very well to the technology industry and to data science. So we start with basic principles being observed at the bottom. And as we bubble up, we start talking about validating technology in relevant environments and labs, operational environments, all the way up to systems being proven in the field. So if we wanted to look at this in a view of how do we do this in a web-centric engineering space, this is what a typical full-stack development process looks like. You kind of come up with the need or the shortcoming, you identify the technology concept, you start programming, you write your tests pass, you push it to a development environment or a dev branch. Hopefully the test pass there. Then you have QA people, and then maybe you do a beta release to your employees if you make your employees use your software. And then once that's passed, you're ready for staging. And then you ship it to prod, and you hope that everything works great. And if you look at how the teams interact, you can really start to see that this process involves more than just your engineering teams. The question is, where do we fit data science in this? And right now, most data science teams within orgs are really at the early levels. We're doing algorithm development, we're doing research on our data, we're maybe building some technology, and then we do some stuff. And then hopefully we get it to running in prod. And then if we're really good about closing the loop, we also do analytics on on whether or not that's been effective. And then we feed that back into the next development cycle so that we continue iterating on our product. So let's kind of go through and talk about data science readiness in this framework. So basic principles observed, that might be like algorithm design. And then we move up to technology concept formulated. That's kind of like exploring our data, doing feature extraction, maybe doing some basic descriptive statistics. The next step, experimental proof of concept, that doesn't need any adaptation at all. This is a lot of what we do in, say, a Jupyter notebook or whatever the R version is. I don't use R. Technology validated in lab. Well, maybe we validate our algorithms against sample data. Once we have the actual code working, well, maybe, hopefully we do cross-validation or some other type of validation when we develop our algorithms. And then we look at the relevant environment. Well, that's prod data. Demonstrating tech in the relevant environment. Well, that's when we start to integrate it with the rest of our technology. And then the last three levels need no change. This is exactly where we want to be. They very accurately describe, in my opinion, what a mature data science product looks like. And we can kind of conceptually separate this into discovery versus delivery. The early phases are discovery, the later phases are delivery. And these are two different skill sets that you need as a data scientist. So let's go through this example of doing a hate speech platform. So maybe you have read a blog post or listened to a conference talk, and you have this great idea for sentiment analysis. So you're at TRL 1. And then you pull some data, and you open up a Jupyter Notebook, and you start doing some basic stuff, like, are we even collecting the data? Do we have messages? Do we have text? Can we even detect hate speech? And you throw together a Jupyter Notebook, and then maybe your next step is you throw together a Jupyter Notebook with cross-validation. And then you're ready for the next level. You're like, all right, I've got this sample data set. It's working great. I want to do it against prod. Hopefully you have an analytics environment, but if you don't, you go to your DBA and you say, I promise, if you give me permission, I won't delete anything. And then if that works, then who knows? There's kind of maybe you staple something together and you can put it in prod. But then you get to the green money part, right? That's where we all want to be. The hard part is that transition between the discovery phase and the delivery phase. And often a lot of that difficulty is because as data scientists, other engineers don't understand our work, so we have a very difficult time communicating with them. So we can do better than this. And my recommendation is that we set intentions and target outcomes to use the model that contracting uses, where you say, by the end of this work iteration, I'm going to have my technology at a certain readiness level. And when you can set that, you know what resources will need to be engaged as you move forward. So to take this example, the hate speech example as a working model. So rather than saying, okay, I'm going to solve the problem, I'm going to deploy a machine learning algorithm, and then everything's going to be great, we have to think of it in terms of work iterations. And so the first one is, can we even solve the problem as stated? Like, do we even have the data? And so this is like early phase work. Maybe we have the data. Do we know how to build the algorithm? Like, does it actually work on our systems? And the answer to this could be no. And then you might go back to your CTO and say, sorry, we need to actually record the data. We don't have anything. But suppose that we actually do. So you might engage your data scientists and your data engineers at this point. And if that passes, we'll go on to the next step. What does a minimum viable product look like? And at this point, you should be engaging people like your designers and your product managers so that they can manage the process of your work as you move forward. And you may even fail at this because you may not come up with a good solution of what a minimum viable product looks like. And that would tell you that you could do all the best machine learning in the world, but you're not going to get to a place where it's going to work because it doesn't fit in with the rest of your product vision. Assuming you can do that, the next question is, how do we build the MVP? And at this point, you need to be engaging other people. You need to be engaging your back-end team, your front-end team, your infrastructure team, and figuring out how things work. And then if that works, then you move on, how do we ship the MVP? And you bring in even more people, and this is where you have compliance, legal, QA, all of that stuff. And what we're doing here is we're engaging people early in the process so that we don't get to the points where we're having difficulties with we've deployed a machine learning algorithm. Why is it now all of a sudden banning all these people from our platform that we didn't want to ban and creating a huge public relations nightmare for us? Not that I'm looking at any social media platforms when I think of this example. And then finally, how do we improve the MVP? So we've deployed something. How do we cycle back and actually take our data, take our knowledge, and then keep identify the weaknesses, identify what it's good at, and then improve this product. And so then we bring in even more teams. We'll bring in our customer relations team. We'll bring in our analytics team. The point is that if you want to be a full-stack data science team, if you're not working with design, if you're not working with customer relations, if you're not working with the other parts of your organization or your client's organization, you're not doing full-stack data science. You're just doing algorithm development. So I have a few minutes left, so I want to wrap up with some takeaways that will hopefully be something that you can bring back to your work for how to actually use this kind of conceptual model to become a full-stack data science team. So the first takeaway is that we have to think of data science as more than just turn algorithms into money. When you start a work cycle, know where you are and know where you want to end. And then engage stakeholders who are needed at your target readiness level at the beginning of your work cycle. So this is as a really good example of this. I worked for an organization that had a fully JVM-based backend. And if we wanted to put anything into our production environment, it needed to be running on the JVM, which is great until we developed all this really cool Python tools. And the problem with that was, well, we could stand up a Flask app, or we could do, some, use PMML, or we could actually just manually code the stuff in Scala. But nobody actually knew how to do anything with our technology. And so we developed all of this cool work, and we spent a ton of time and energy in it, but we didn't have anyone that could actually support that work. So if we wanted to stand up a Python microservice that did all of this, cool recommendation work, we actually would have needed to hire somebody that could maintain a Python microservice in production. We needed to hire DevOps people to handle the deployment, or we needed to do on-call shifts as data scientists, and we weren't paid for that. So we need to be able to engage your stakeholders early on. If we were able to do that, we probably could have done a lot better, rather than say, hey, we built this model, now ship it, and everyone's like, well, we don't know how. Another key takeaway is failure is normal. We should be failing as data scientists very often. If you're not failing, you're not innovating, in a sense. Most of the time, we're going to look at data and we're going to say, maybe I can get a pattern out of this, maybe I can build a model out of this, and then it's not going to work. And we have to keep iterating. This is a normal research process. And so you can't just say, I'm going to start at the early level and I'm going to develop all the way up to the end and it's going to be great. If you're not having some stumbling, then I really question, whether or not what you're doing is actually effective. So failure is normal and the process is not monotonic. You should often have to reset yourself to a lower technology readiness level as you do this work. Different readiness levels also require different skills. This is a critically important thing as we look at building data science teams. People who are good at computational math may not be good at visualization. People who are good at feature engineering may not be good at cloud management. So what you want to do is realize where people's individual strengths are and use this as a roadmap for personal development. For example, I am terrible at visualization. I can do it. It takes me 4 times longer than it should to make an effective visualization. But I'm very good at math. So my strength is not in building a dashboard or building a front end to view the data. My strength is in understanding the algorithm, which means that I should be looking towards people who are good at that to complement me in my team. And then finally, identify weaknesses in your stack. Where are your barriers? Where are your readiness level barriers? I talked to somebody yesterday who developed some really cool algorithms, and they wanted to have a really cool front end to do the visualizations, and they're like, but we don't know how to do this. We're kind of like doing this thing where we're hacking things together, and we just don't have the time to build out that technology. So if those are your barriers, you need to be able to identify them, and that's where you should focus your hiring or your professional development. And then finally, what are you asking your data scientists in your organization actually to do? Are you using their best strengths? Are you using them, do you actually have people that can get you through those barriers and communicate with the people that you need to in your organization to start building data products? That's really all that I have. Thank you very much. I think there's a couple minutes left for questions, and yeah, hopefully this will help some of you bring your products and actually set them loose in the world in a positive way that makes a difference. So, thank you.